Hey guys. So I'm gonna do the some of the homework on chapter 11. So our inference estimation. So this is the this is our introduction chapter into inference. Several of our problems we deal with inference that deals with proportion, and then also with mean. So we're gonna do a few of these problems together, and hopefully that will help you be able to figure out how to do the rest of them. Alright, so let's start with question 1. So question 1 says that a study on financial aid during 2014 to the 2015 school year used a random sample of 2,000 Georgia State University students. The findings were 1710 students received grant aid, 290 did not receive any form of aid, and then the average amount of grant aid received was $8,595. Okay, so that's all of our information, right? Then they ask, what is the point estimate for the proportion, so we're looking at proportions, not mean, of all college students who received student aid. Now remember here, what does point estimate mean? Well, point estimate just means, okay, what's the single value that we know that does the best at approximating or estimating the value for all college students who received student aid. So in other words, it's the sample proportion is going to be your point estimate for, or your best point estimate for, the proportion of all college students, so the population proportion. Okay, so how many students received financial aid? It says we had 1710 students received grant aid. So then that means, if we're looking for our p hat, they say there's 2,000 total. So 2,000 students total. And then it says 1710 received grant aid, right? So that's what we want. So in other words, your p hat, 1710, this is what you want, divided by your total. Remember, that's our caveman definition of probability. Caveman definition of probability is what you want divided by everything, right? So everything you're studying. So remember, that's our caveman definition of probability. So here, we want all the students who have financial aid. Well, that was the 1710 it said, right? And then what's everything we're looking at? Well, that's all of the people that we're studying. In fact, that means it's our n, right? So it would just be your 1710 divided by this guy, by your 2000. Okay? So that's all we have right now. So our best point estimate in this case, so our best point estimate for population proportion P is your sample proportion P hat. So you would copy this, throw it in there, and you see it's the same thing. Now part 2. Now they say, what is the point estimate for the mean student grant aid received? Now this one's a lot easier, right? Because the mean, you don't have to actually calculate anything unless they give you actual data. But here they just give us our measures of center and a proportion. But here they give us the average amount of grant received was $8,595. So you guessed it, this right here is your best point estimate. So if you ask for the point estimate for the mean student grant received, the best point estimate for the population mean of student grant aid received is your sample mean. That is the best point estimate. So you'd copy that and put it in there. Please, when you guys are doing this for homework or tests, pay attention to this. Don't put commas or any special symbols. That could help a lot with any frustration you might have. If you put it in there, it could count it as wrong, and then that means all of your work that you did, if you did any work for this part, all the work just because of the symbols could make this wrong. So please pay attention to what they say here. Alright, so now let's get a little more interesting. So the amount of money, so looking at question 2, the amount of money a family spends on a night out for dinner in a certain city has a standard deviation. Now look at this symbol. You have to know these symbols. What is this symbol This is sigma. This means it's the population standard deviation. If a random sample of 100 families is found to have a sample mean amount spent about $59, this is our, now X bar, remember what that is? That's our sample mean. Wants us to estimate the population mean with 90% confidence. Now it does give you the z-score here. It'll give you the z-score, and I think it does it for a lot of the problems. I'm not sure if it does it for every. It doesn't look like it does it for this one. But for a few of these problems, it tells you the z-score, so you don't have to actually calculate it. But for the sake of consistency, I'm going to calculate it every time, so that way you guys can see it consistently, and you guys will, be able to do it yourself. All right, so let's start copying over this information. So here's proportion. I'm gonna hop over to mean. Okay, now it says, just doing our data. It says 100 families. So that means we're looking at 100 families. That's our sample. Our X bar, they say, is 59.53. So X bar, 59.53. Okay, and then they said standard deviation for the population, 22.98. So 22.98. All right. Now again, I'm looking at the confidence level. Confidence, they say, is 90%. So we have a 90% confidence level in decimals, 0.9. Now they give you the z-score, right? Because this z-star is just your special z-score of your confidence level. So you don't have to calculate this. You can just type it in, but I'm going to. All right, now what's our alpha? Remember, alpha is our error level. So if we're 90% confident about our answer, that leaves us 10% for error, right? We have a 10% chance of our mean, our population mean, not being in our confidence interval. All right, so here we go. So the z-score, remember this formula is the same all the time. Norm.s.inverse, and then your probability. The probability is going to just be a special form of your alpha, so a special form of your error. It's just 1 minus your alpha, so this 0.1, divided by 2. Remember, because in a confidence interval, we're trying to find an upper bound and a lower bound for our population mean using our sample data. So if we're trying to find an upper bound and a lower bound in our interval, this means that our error, we could possibly go too high or too low in the interval. So that's why we have to take into consideration an error on both sides of our tail. So both sides on our distribution. So that's what this guy does. That's why you divide the alpha by 2, remember. Okay, so now we can find our margin of error. Now remember, this formula here is simply m is equal to your special z-score, then times, so your special z-score times your population standard deviation divided by square root of your n. Remember, it's this guy. Okay? So what I do, I click on my z-score times, let's go ahead and get in a good habit of using parentheses. I click on my population standard deviation, divide by the square root of my sample size. That's my n. And remember, since I began with a black parenthesis, I have to end with a black parenthesis. Make sure you have that color agreement. And there we go. My margin of error is about 3.78. All right? So remember here, to find your lower bound and your upper bound for your population mean mu, it's really simple, right? Once you find your m, which is simply your special z-score times your sample standard deviation, remember that's what this guy is, that's all you're doing. So we know how to do this already. So what we're doing is, for your lower bound, well, it's what happens when your x bar is smaller, right, than the middle part. So that's why we're subtracting our margin of error off. So click on your x bar, minus your margin of error. This is your lower bound. Okay, now let's get our upper bound. Click on your x bar, and then add your margin of error in. And there we go. So here, we're saying that we have, since this is a 90% confidence level, we're saying that we have, with 90% certainty, or we can say that with 90% certainty or 90% confidence, that our population mean is between these two values. So that's how we read this problem. So we can say with 90% certainty. Remember, that's your certainty. Remember, that's your confidence level. It's a whole reason we do confidence level here is we're not 100% certain ever. We have to do the our certainty this way. So with 90% certainty, that population, so the population mean mu is between our lower bound, so 55.75 approximately, and 63.31 approximately. That's how you would read this problem. Okay, so that's the population mean. So that's what we would do. It doesn't really ask us for that. It just asks us for this bound. So you just copy this guy over, throw him in there. See 55.75, and then your 63.31. Throw those guys in there, and we're done. Okay, this problem is the exact same, pretty much. So you guys should be able to do this. Question 4. It's much of the same. It's another one. It looks like they're just kind of changing the confidence around, right? They're just changing the confidence, changing the numbers around a bit. So, yeah, what I would suggest is, practice these guys yourself. Now you guys should know what to do. These are the exact same problems as the one we did before. All right? Now here are just some concept questions. So, which confidence interval will offer the most precise estimation of mu? Okay, so let's look at this. So here I have a confidence level of 90%. Now look at these two guys. Okay, let me show you this. Here's the difference between the two. So in other words, this is kind of like the distance, or I'll actually put that there. In fact, I can do it down here. So distance between lower and upper. Okay, so let's look at our distance between our lower bound and our upper bound, and I'll put it right down here. So check this out. I'm going to click on my upper bound, subtract off my lower bound. So look at this, it's about 7.5. So the distance from my lower bound and upper bound, I'm saying that mu can be any one of those approximately 7.56 values. So there's 7.56 approximately units between my lower bound and upper bound, and mu can be any value within that distance. So that's a pretty large span, right? Well, check this out. So that's with a 90% confidence level. Let's try it with a 95% confident level. So remember, that's 7.5. Ooh, look at that. So as soon as I increased my confidence level just by 5%, and look at this. Now instead of it being the distance being 7.5, now it's 9. And see, we can do this again for 99. Now it's up to almost 12. So you can see that the more confident you get, the distance between these two numbers is going to be greater. And that's because, remember that the confidence level is saying, hey, we've got a 99% chance that my population mean is between these two values. So the more confident you are, the greater this distance, because it's going to have a better chance of including your population mean. But why is that a bad thing? Well, the larger your distance between your lower and your upper might increase the chance that mu is in there, but you have a lot more values to choose when you're actually trying to identify your true value of the mean, of your population mean, right? So this means that there's a lot more values our population mean could possibly be. So in other words, it's not going to be as precise, and that's what I got into this inverse relationship. Remember, there's a negative correlation between accuracy, I think they use precision in this, between accuracy and confidence. So the more confident you are, and remember that just means like one variable goes up, variable goes up, the other goes down, right? That's what the inverse relationship means. If one of them's going up, the other guy's got to come down. So in other words, if accuracy is going up, your confidence is going to go down. So this will help us with these concept questions. So here it says, which confidence interval will offer the most precise estimation of mu? So remember, it's precise. We're looking at precision here, not confidence. So the most precise estimation of mu would be the one that has the smallest distance, right? So in other words, it's going to be the one that has the smallest confidence level. So that would be your 90%. Now it says, which confidence interval provides the most amount of confidence but the least amount of precision? Well, remember we said that the largest distance between my lower and my upper happened with the higher confidence level. So here, my confidence level of 99% is the biggest one, which means that I'm going to be more confident that mu is in there, but it's going to be a lot less precise. So 99%. Okay? So these are the same kind of things. Which of the following confidence interval provides the most precise approximation of mu? Remember, precise just means the smallest distance. So find the smallest distance between the two guys. This is only 0.14 distance. This one is like 0.3. So find the smallest distance between the two, and then you have that guy. Then it says, which of the following confidence intervals provides the most confidence in the approximation of mu? Remember, the most confidence means it's going to be the largest range. So find the difference between the two. Find the difference that is the largest. This one will be the largest difference. So just doing what we did before I wrote this negative correlation. So just do that same process for these guys. All right. Question 9. This guy looks the same, right? So 99% confidence interval for the mean number of hours in video games. Now it says played per day was found to be 1.7, 5.7. Okay, so slightly different. So now it says this is the confidence interval. It gives us the actual interval values, and we have to go back and find our margin of error. Okay, well this one, you just kind of have to think about it. So you can go back and do the formula and whatnot, but think about it. Think about this. If I have 1.7 and 5.7, and I want to know what the margin of error is, whatever the sample mean is that I have, I'm adding my margin of error, the same number, to it to get 5.7, and subtracting that to get to 1.7 as well. So all you have to do is first find your mean. So let's find our mean in this problem. So my mean would be the average between these two guys. So what I do is, it was 5.7, 5.7 and 1.7. So 5.7, 1.7, and let's average these guys. So average. Right? Because if I'm adding m and subtracting m, that means that if I take the average, I'll find the middle of them. So in the middle of them, this is going to be my x bar for this problem. Okay? So remember that my lower and my upper, well, they were 1.7 and 5.7. So if I'm looking for my m, this is all you have to do. Take your larger value, subtract off your 3.7, and voila, you have your margin of error m. So I mean, you can do it this way too. So like if you want to use your lower bound instead, this time take the larger value, subtract from your lower, and you get the same thing, right? So either way, but that's how I would do that problem. Pretty simple. Because the confidence level and the sample and all that stuff that it gives you, that doesn't matter. You can just use that simple process to find your m. Okay, so here, do the same thing. So 158.9, 165, I have 69.5. So 158.9, so 158.9, okay, so 158.9, and 169.5. 169.5. Oh, wrong place, sorry. Should be down here. Okay, and then just make this, so like our x bar is up here, right? Find the average between the two. So same process we did before. Find the average between these two guys. Your mean, x bar, is going to be 164.2, and your margin of error was, well, take the larger one and subtract from the smaller. So take your upper, subtract off your x bar. This is your margin of error. Right? Oh, oops. Well, that's not what we needed to do. Well, it's good practice anyway. So, but here it says, which of the following confidence intervals is the most likely if the sample size is increased? See, this is why you need to read the problem. So that was me giving you an example of what really not to do, I guess. Alright, so it says, which of the following confidence intervals is most likely if the sample size is increased? So remember what I said in class. I was saying that the larger your sample size, you're going to get much better approximations. You're going to start zeroing in on your population mean. So your confidence doesn't matter. The way that we can change and make our answer more accurate using the same confidence is just take more samples, right? Make your sample size larger. So in other words, if you increase your sample size, then our distance between these two should be smaller. So just look for the one that has the smaller distance. In this case, it's this, right? This one only has 0.2. This guy has a large distance. This one also, oh, sorry, not 0.2, 5.2. This guy has a fairly large distance. This guy has a large distance. And this guy has a larger distance. So then this one has the smallest distance. So if our sample size increases, oh, yikes, lost it. If our sample size increases, then that's exactly what we're going to get. Okay, determine the 99% confidence level if the sample size were quadrupled. Okay, now this one can be kind of tricky, so let's do this one together. All right. Well, crap, I could have just left that stuff there. All right, so here we have a 99% confidence level. Now we're going to do the same process here. So 222.9. So 222.9, and then 281.3, so 281.3. Okay, now find your x bar. Remember, this is how we find it. So x bar, oops, x bar, average, and then these two guys. Yes. Okay, these I have to change because I need to go with this. Take my upper bound, subtract for x bar, and I get my m. Okay, so that's my margin of error. Alright, so now I've got to use the formula to determine, well, what happens if my sample size were quadrupled? Alright, let's check this guy out. So my sample size. So remember the formula here for m is equal to z star times your standard deviation, so standard deviation for population divided by square root of my sample size. Now let's look at this. So I don't even know, well, I guess we do need to calculate this stuff, but well, you'll see what to do. Alright, now if my sample size were quadrupled, that means that my n is going to get multiplied by 4. Right? So my sample mean remains the same, they say, but my sample size was quadrupled. Alright, so here we go. So I need to find now what happens to my m, because the m here in this case doesn't matter. Okay, so you do m equals, your z star doesn't matter, your standard deviation, that doesn't matter either. You don't need to know this stuff. But then you have the square root. Now, if I am quadrupling my n, I'm doing 4 times n. Alright? So let's look at this. So this guy goes in our denominator, right? So this would be a lot easier for me to show you on paper, but I have to show you in Excel because that's all I've got. So this is the square root of 4 times n. What's the square root of 4 times something? Well, you can split these guys up, right? Anytime you have multiplication inside a square root, you can take the square root of the individual values. Well, square root of 4, that's just 2, right? So m is equal to, do the same thing here, but now my square root of 4 comes out, right? Square root of 4 is 2, so now it is 2 times my square root of n, right? Okay, so it's just standard deviation, your z-score, and your m. They don't matter here. We just want to know what happens to our m if we have 4 times our sample size. Okay, so this is just like a 2 in the denominator, right? If I multiply both sides by 2, then I get rid of this 2 in my denominator. So it's 2 times m. Okay. Square root of n, multiply this guy, 2 should be 1 over 2, multiply both sides by 2. So multiply both guys by 2. Your m gets multiplied by 2. Oh, that shouldn't be the case. Huh. So let me see. If my sample size were quadrupled, that's 4 times that. Oh, that's right. Oops. Okay. So my m here, so it's only if I wanted to solve for one of the other variables, but I want to keep this 2 on this side. So in other words, remember, here, this whole formula is m, just with this 4 here. Now it's like it's m, but then what happens now? The only difference is we have an extra 2 in the denominator. So it's almost like it's m divided by 2. So in other words, our m gets cut in half if we quadruple our sample size. So it's almost like it always gets cut by square root. So m gets cut by square root of a if square root of a, we'll just say this, gets cut by square root of 4 if sample size is quadrupled. Does that make sense? So all you have to do, if it's like, if your size, gets, I don't know how to say it, but like, if you multiply your sample size, like you take 9 times as many individuals for your sample size, it'll be the square root of 9. That's how much it'll be divided for. Okay, so let's just do that. So this would be like kind of our new lower and our new upper, right? So just do this. Click on this guy, divide him by 2. Click on this guy. Oh crap, nope, that's definitely not how you do it. Let me see. So my m gets divided by 2. Oh, that's right. It's not these guys divided by 2. So yeah, you do have to find your m. So what was my m? M is just the difference between my x bar and my lower bound, right? So this is my m. Well, now my m gets divided by 2. So m divided by 2, take your old m that we found. So I shouldn't have gotten rid of him before. Divide by 2. Now this is what I'm going to do for my lower and upper. So remember, the way we did this before, take your x bar, for your lower bound, subtract from your m. In this case, it's our new m, so m divided by 2. And then take your x bar and add m divided by 2. Yep, sorry about that. I confused myself there for a second. But this is the process, right? So this will be our new lower and our new upper. So you copy that, throw them in there, and we see we got the same thing. So 237 and 266, 237, 266. All right? So see, just like I said here, so what's going to happen here? Given a 90% confidence interval and population standard, what would happen to the margin of error if the sample size were multiplied by 9? So kind of like what I said, if it was quadrupled by 4, then the margin of error became smaller got reduced by 2, right? So that means that you'd have to divide that, divide your margin of error by 2. Well, if it were multiplied by 9, your sample size were multiplied by 9, take the square root of 9, it's 3, so your margin of error would be divided by 3, or divided by the square root of the number it gets multiplied by. Okay, so hopefully that helps clear some of that confusion up. Okay, this guy here, just concept question. We've already been going over them, and so on. So let's see, how many ticket prices would be sampled? 99% confidence with a margin of error, m is equal to 3.4. Alright, so this one is just a backwards solving problem, so you guys should be able to do this. It's just algebra, right? So we know that this is our formula, right? Well, it gives you m. We can find z star, because it's I think I said 99% confidence. Yeah, so 99% confidence. They give you your population standard deviation, so they even give you the z-score, and they give you your margin of error. So the only thing you don't have is your n. So go backwards and solve for n. That's all you have to do. It's not too hard, just a little bit of algebra. And unfortunately, algebra is kind of tough to show on Excel, so I won't show you how to do that. You guys should be able to do it. Okay, this looks like this is the same thing. The maximum cost is 17,000. Approximate the population standard deviation sigma. It's another one, right? So basically, they're kind of beating you to death with this formula. So they're going to give you a means to find your margin of error. They'll give you a way to find your x bar, and when you find your x bar, you can find your margin of error by its given lower and upper. So you find your m, you'll find your z star, and you'll find, or it'll be given to your n. Find one of the missing pieces. So in this case, it's standard deviation. So again, it's just algebra. So you guys should be able to do that one yourself. Okay. Here's a proportion. 90% confidence level. Poll contains 7,167 votes. Alright, find the 90% confidence level for this. Okay, so this guy here, it's the same problem. It's like the problem we did earlier, right? Okay, and it looks like this one is the same. So this is a 90% confidence level, 95% confidence level. And this one, I'm not sure what happened here. Let me check this out again, because I did it and I got the right answer, but when I put it in, for whatever reason, I put it in incorrectly. Let's see, so they're made in USA. Just says a recent poll asked if Americans only buy products that are made in the U.S. Let's get this guy together. So find a 95% confidence interval to estimate the population proportion who only buy products made in the USA. Okay. So let me show you this, just so we can get this right, because I know how to do this. I just, for some weird reason, I don't know if I put it in wrong or something, but something happened, and it said I was incorrect. So let's get this problem fixed. Okay, so we want a 95% confidence interval to estimate the population proportion who buys only products in the USA. Okay. So we take this data. So this data says, okay, do you only buy products that are made in the USA? So think of this almost like a computer, right? A computer is 0 if it's off or if it's false, right? So we're talking binary here. Binary, if it's 1, it's true. If it's 0, it's false. So if you're answering the question, do you only buy products that are made in the USA? 1 means yes, 0 means no. Okay, so here's our yes and here's our no. Now this is an awful lot of things to count. Like, this is a long time. So what you're going to do, use COUNTIF. Use the COUNTIF function. Now it asks for your range and your criteria. So the range, that just means all of these numbers. So it goes all the way down to 101. Okay, so it'll be A2 to A101. Now it asks for criteria. Okay, so this just means, all right, what am I counting? Well, count it if you see 1. Okay, so in other words, that's what it's saying. If you see this symbol 1, count it. So here we have 38 ones. Okay, so now we want no's. Do the same thing. No, remember, is 0. So your same range, so that's the A2 to A101. And then criteria is 0. And this makes sense, right? Here we go. 38, 62. So your total, sum these guys up. So my n is 100. I don't know if they gave that in the problem or not. Doesn't look like it. So yeah, 100 total people. Now it asks, find a 95% confidence interval to estimate the population proportion who only buys products made in the USA. Alright, so, in other words, this is our n, right? Oops, not no. It's our n. So our p hat, so only in the USA, that'd be your total of yes divided by everyone, right? So our p hat is should be 0.38, so population who only buy products made in the USA. Okay, my z star, it gives you the z star, but if in case you can't find it, remember we need our confidence level, we need our alpha. Confidence level 0.95, because we're doing a 95% confidence interval. Alpha 1 minus your confidence level. Then find our z star. So z star is norm.s.inverse 1 minus your alpha divided by 2. So we use the z-score 1.96, right? And that's exactly what we got here. Now our margin of error. Okay, so our margin of error here would be our your z times your p hat times 1 minus p hat. Then you divide, so this is our numerator, right? Divide by your n, which is our 100. So 0.0461 something. Okay, this is strange. It looks like I'm going to get the exact same one. So this could be an error. Trying to find a 95% confidence interval to estimate the population proportion who only buys products made in the USA. So this could be an error, possibly, because 2.85 and 4.75. So I mean that makes sense. Problem is though is it's going to be a lot smaller. So my lower and upper. Okay, so let's do this. So we do take our p hat, subtract off my m, and then take my p hat and add my m. So see, I got this. Okay, so then that's 1 minus, what did I do wrong? How did they get this? 1.96, is using 1.96 really that different? No? Margin of error for proportion, right, because our p hats, okay, divide by 100. This doesn't seem right. So p hat, they said, is 0.38. We got that right. Okay, but how did they get a margin of error like this? This doesn't 0.09, 0.0. Huh. Yeah, this might be an error. So if you guys encounter this too, yeah, if you guys 0.38 times 1 divided by, I mean, let's see. Let's just make sure I didn't make a mistake. This is my z. Oh, wait a minute. Aha. Wait, did I really not do that? Oh my gosh. Okay, so that was the error. So now it's good. You guys can see that I make errors too. But look at this. I forgot to put the freaking square root in the problem. So make sure you don't do that because you will definitely get the wrong answer. Okay, so remember, my m for proportion is z star times square root p hat times 1 minus p hat divided by n. All of that in the square root. So sorry about that, guys. Yeah, make sure you square root it, because if you do not square it, you will get the wrong answer. Okay, so it is definitely not an error. That was an error on my part. So there we go. So at least now that I did the error, you guys will see how you're supposed to do it. So make sure that you get the right answer in there. And I think that that's what it says the right answer is. So I go to solution, and I see 0.285, 0.475. So we go back to my other Excel. Where's the other guy? Should be right here. Yep, 0.28 and 0.475. Yep, okay. So got the right answer for that one. Okay, so just make sure you don't make that mistake. You should be fine. Okay. I think that's really most all the problems now. So here, okay, so this is the ultimate test. So it looks like I did this one right this time too. So I must have just forgotten the square root in that problem, and then did the square root in this guy. But yeah, make sure that you do the right process for question 21. Do it correctly. That should be, and then you guys should be good. And then here, when using confidence intervals, in what way can we realistically increase the precision of estimation of P? Well, when using confidence intervals, how can we realistically increase the precision? The one answer you should always have, as soon as it says increase precision, it's always the absolute best. Like, you could always make it better if you do this anytime you're studying anything in statistics. If you increase your sample size, you will get better answers. So you will get closer results, more accuracy. So this will always be an answer. If it's like, how can we do something better? Well, increasing the sample size. That always helps. And then, of course, the other thing, decrease the level of confidence, because we want to have more precision. More precision means smaller level of confidence, right? That means less values that our mu can possibly be, so a smaller range. All right, so you guys do this one same way before. You download this, and it's use the COUNTIF. 1 is yes, 0 is no, and then make sure that when you guys do this, that you use that square root. Don't forget it. Okay, don't forget that square root. It'll be like the you know, whatever that's called. Remember the Alamo, but instead it's remember the square root. And that's all I have to say for you guys. So yeah, have fun with the homework.